Hello, welcome to the lecture on Fourier analysis. Today I'm gonna talk about specifically about Fourier transform that provides us a tool to analyze signals in frequency domain. So why frequency domain? Okay, well, before going into details about Fourier transform, let me draw your attention to the big picture on the concept of frequency domain. Uh, as you know, mobile phones have become a part of our daily life. When we talk with somebody on the mobile phone, our voice or speech is input signal, and this speech has to be coded in order to effectively use the limited bandwidth provided by the system. Human voice typically varies between 100 Hz and 4 kHz in the frequency. In cellular communication systems, signal bandwidths are important because the overall bandwidth provided in these cellular systems are limited. Here the term bandwidth means the frequency range of the signal over which the signal magnitude spectrum is non-zero. When we look at the evolution of wireless systems, they are called as different generation systems. In the first generation analog system, the signal bandwidth is 30 kHz, and in the second generation system, this bandwidth increases to 200 kHz for instance, in GSM system. In the third generation wideband code division multiplexer system, the signal bandwidth is 5 MHz, and in fourth generation long-term evolution systems, signal bandwidth may go up to 20 MHz. Another example on the importance of the Fourier frequency domain concept is the filtering in signal processing. As you may be familiar with filtering concept, the traditional filters can be low pass, band pass, or high pass filters. And low pass filters let the signals smaller than the certain frequency, such as cutoff frequency, pass through it, while suppressing the signals above this cutoff frequency. And we design the filters according to some set criteria in the frequency domain. In radio broadcasting, we listen FM or AM stations. Here, FM and AM means the modulation type used in the system. When we say modulation, it means the manipulating the frequency or amplitude of the carrier signal according to the input message signal. Okay, at the later slides in this lecture, we will cover AM modulation in detail, and you will have better understanding of the concept when frequency domain is involved. So, frequency domain analysis is an alternative way of viewing or analyzing the signals. Many problems, of course, many problems in frequency domain can be easier compared to time domain analysis to understand and solve the problem in this frequency domain. And the question is how to obtain the frequency domain representation of the signal. One answer is the Fourier transform, and in this lecture you will learn in detail the frequency domain or analysis based on Fourier transform. So let's go into details of Fourier transform. To start the discussion, let us define a time domain signal x of t. Here the signal x is lowercase letter, and we denote the Fourier transform by symbol f accompanied by an arrow. The transform is capital X of omega, and of course that is in frequency domain, and lowercase x of t is in time domain. Omega is the angular frequency in radians per second, which is also 2 pi times f, where f is the frequency in hertz. Fourier transform is obtained by Fourier integral. The Fourier integral is defined as integral from minus infinity to plus infinity, lowercase x of t e to the power minus j omega t dt, and that whole thing is the capital X of omega. So Fourier transform basically tells us about the frequency measure or frequency content of the signal. However, we cannot obtain the information such as the frequencies occur in time by the Fourier transform. Like every transform, we have the inverse Fourier transform. In the inverse Fourier transform, given the capital X of omega, that is the Fourier transform, we obtain time domain signal x of t by the inverse transform, that is denoted by f to the power minus 1. And the integral form of inverse Fourier transform is the integral from minus infinity to plus infinity, capital X of omega e to the power j omega t d omega, and the whole thing is scaled by 1 over 2 pi. Okay, the equation regarding inverse Fourier transform is pretty much similar to the forward Fourier transform. Integrand function is in omega domain, but notice that we put positive sign at the power term of exponential function. And that term was negative sign in the Fourier transform integral. Also notice that the 1 over 2 pi term comes in front of the integral.